The atomic force microscope, or AFM, was developed around 1986. It is also known as a scanning force microscope or a scanning probe microscope. The microscope works by having a cantilever, a beam or girder which sticks out of something and is only anchored at one end, with a sharp tip on the free end. The cantilever is then either moved over the sample or the sample moved under the cantilever. A laser is shone at the top of the cantilever and this reflects into a photodiode. The photodiode measures the distance which the laser moves as the cantilever interacts with the surface of the sample and uses this to construct an image. That might be a lot of information to be given at once, but can be easily simulated with a model. Here's one I made earlier. The laser pointer contains a laser diode. This arm is the cantilever. The drawing pin represents the sharp tip on the cantilever, and the mirror on top allows the laser to reflect off of the top of the cantilever. As the AFM moves over the sample, the tip interacts with the surface as shown here. The laser reflects off and can be measured, in this case by plotting the path which the laser took. Mine is slightly less than accurate as this is quite a complex model to operate single-handedly. We can join the points up to create a magnified version of the surface scanned. The cantilever would then be moved forward slightly and the process repeated. This also allows the microscope to build up a 3D image, unlike electron or optical microscopes. Another way they work is by using the same process, but by moving the sample instead of the cantilever. This program simulates an atomic force microscope. In this example, the sample is moved under the cantilever. The height of the sample can be adjusted, and so can the scanning speed. The gain is used to adjust what the AFM does with the interaction between the cantilever and the sample. With no gain, or the gain on minimum, the microscope just continues scanning the sample. If you set the reference and then increase the gain, the sample will be moved up and down to keep the laser lined up with the reference point. The amount that the sample has to be moved is then measured to produce the same result. The way the force is measured is done in a number of ways. The main processes are either measuring how much the cantilever moves as it is dragged across the surface, or measuring the force of interaction with the surface. In the second instance, the tip does not actually touch the surface, but at the scale it is working on, the atoms put forces on each other, and this is what is measured. This video shows a real AFM as used by students at Bristol University, England. This is the cantilever. This is the laser diode. And this is the quadrant photodiode, more on that in a minute. This is a video camera and microscope which allow people to see where the cantilever is in relation to the sample. This is the quadrant photodiode. This has 4 photodiodes which detect the laser light. When the laser is shone into a diode, it creates a current. As the light moves around, the current moves between sections, allowing you to measure how much the laser is reflecting from the cantilever and therefore how the cantilever itself is moving. The benefits of an atomic force microscope are that the sample does not have to go through rigorous preparation before being observed, and that the tests do not need to be carried out in a vacuum, unlike electron microscopes. Also, the fact that AFMs can build up 3D images is hugely beneficial. Unfortunately, AFMs are currently limited in the size of the sample they can scan. Also, there are limitations dependent on the shape of the tip on the cantilever, as demonstrated in this final computer simulation. If the tip is an awkward shape for the surface of the sample, then the image could be wrong. In this example, the tip is a bit rounded and is quite right across the middle. The blue line shows the surface to be scanned, which appears when I check this box, and the black line shows the surface as scanned by the probe. However, this issue can be solved by using a cantilever with a different shaped tip. And that is basically how an atomic force microscope works.